Consider this line on the 2D plane. It's pretty short, right? Well, not exactly. If we rotate our perspective, we can see that this line was actually a 2D projection of a line sitting in 3D space. Okay, let's try again. What about both of these lines? There's an obvious intersection here, but again, if we shift to a 3D view, we realize that this intersection was actually just a result of occlusion. With only a 2D view, it seems impossible to figure out the depth of a given point, right? The question is this: given a collection of 2D strokes forming a sketch, how can we reconstruct these strokes in 3D space? This problem was tackled by Felix Hähnlein in their 2022 paper, Symmetry-Driven 3D Reconstruction from Concept Sketches. Their approach follows a two-pass system. The first pass aims to create a basic scaffold using existing construction lines and clear global symmetries. In their second pass, we focus on segmented building blocks of the sketch, enforcing local symmetries while using our global scaffold as a reference. Before we start, we need to find the three global, axis-aligned planes in the sketch. This can be done in a multitude of ways, and for this paper, a vanishing point detecting algorithm is used. With these planes, the algorithm selects one of them and attempts to enforce global symmetry across it. How? By identifying candidate pairs of strokes that could possibly be symmetric reflections of each other. Imagine two strokes, A and B, and a proposed plane of symmetry between them. This pair is said to be a candidate pair if the triangles that these lines form with the vanishing point align geometrically, given some room for error. Now this makes intuitive sense. If these two strokes were symmetric in 3D, we'd expect them to lie on the same similar triangle. We can now reconstruct the small subset of strokes to form a simple scaffolding. Given two strokes, as well as their proposed plane of symmetry, we first build two planes connecting each stroke in the candidate pair to the perspective camera. We can then mirror one of these planes about our original plane of symmetry. The intersection between these two planes gives an infinite line in 3D space, which we can project one of the strokes onto. We can use a symmetric approach to obtain a 3D projection of the other stroke. Now we focus on the second pass, using the local symmetries of segmented building blocks for non-globally symmetric strokes. First, we obviously need some way to actually segment our strokes into locally symmetric blocks. This paper leverages an interesting heuristic about the way artists sketch to do this. People tend to draw one symmetric part at a time. Now, by analyzing the density of candidate pairs along a histogram, we notice several peaks representing different blocks. We can split these peaks along local minima to form groups of locally symmetric strokes, our building blocks. For each block, we test different triplets of local symmetry planes, offset from our global one. Each triplet is put through an optimization problem using a scoring function to determine how well it fits with the block. This function rewards strokes with multiple symmetries, strokes that support each other, strokes that are close to the group average, strokes that are strongly anchored, and strokes that cover multiple different strokes. Each heuristic is associated with a weighting term to prioritize certain constraints over others. Each block is then reconstructed in the order they were drawn using the local symmetry planes we found. Our scaffolding is used as a reference point to anchor blocks to, and subsequent blocks are anchored to each other. This gives us our full, final reconstruction. The results for this method are pretty good, especially when compared to previous approaches to this problem. Here are just a few examples of some reconstructions, along with their initial input sketch. Of course, this method isn't infallible, and the paper notes limitations in handling oversketching under very strong perspective, as well as a dependence on finding the correct initial candidate pairs. But overall, this is a neat way to bring 2D sketches to life and opens up many avenues for future 3D reconstruction techniques. Thanks for watching.